have 5 carbons in this guy, so there are going to have to be 5 carbon dioxides on the other end. Okay. Secondly, we've got 12 hydrogens there, which means we're probably going to come out with about 6 of these guys here on this end. Okay. Now we've balanced out carbons and hydrogens. We've got 5 carbons, 12 hydrogens on this side, 5 carbons, 12 hydrogens on this side. Now we just need to figure out the oxygen. On this side now we know that this is locked down and this is locked down. We just have to figure out this. We've got 3 pairs of oxygen here and 5 pairs of oxygen here, so it should be 8 pairs of oxygen there. Very good. Okay. How many molecules of products are going to be formed from this? So let's say you start with 1 molecule of pentane. It looks like you're going to walk out the other side with 11 molecules of carbon dioxide and water. Okay? All right. Assuming 8 molecules of oxygen, of course, but oxygen is considered to be basically irrelevant in this case. Okay. All right, moving on. They may also ask you to do, on the conceptual side of things, the non-calculatory, they may ask you to do a lot of more sort of Lewis structure-y drawing diagrams of different things. So let's take a stab at that, shall we? Yeah, okay. Lewis structures, and these again, you just have to kind of take a whack at drawing them as best you can. BF3 and N2O is what they want us to do. Okay, BF3, N2O, good, okay. BF3, let's start off with that one. Very good, okay. Think about what's happening here. We've got 3 fluorines around a central boron ion. Each of these fluorines is going to have 7 free electrons. And then, so we've got 3 pairs and then 1 which is going to form a pair with the boron right there. Okay? Boron only has 5 free electrons, so this actually works out perfectly for boron right there. Okay? Next up, for N2O, okay, there's a couple different ways that you can write this. Okay, first of all, we've got the nitrogen is going to have to be connected to each other, right? Nitrogen wants to make 3 bonds, oxygen wants to make 2. So it could be the case we end up with nitrogen and nitrogen go ahead and form a triple bond and leave oxygen dealing with itself right there. All right, now you're going to end up with a negative charge on this guy and a positive charge on this guy, but that's okay. It's not the end of the world. Next, you could also have these guys in a double bond, okay, but that's going to tend to leave this nitrogen is going to need to have an extra pair of electrons to cover that. And then you got a double bond on the oxygen over here, so that's more or less okay. You could also have a form where these guys have a single bond, right? The problem is that these both have a weird situation, nitrogen having 4 bonds, which is not what it normally likes to do. Okay, this one, this guy is only forming 3 bonds. All right, leaves oxygen in the loop, and then this guy over here just has to pick up a whole bunch of nitrogens in order to make it work. Important to remember that these are all interconvertible versions of each other, and probably if you looked at them, you'd find all 3 side by side. Or if you looked at one for long enough, it would just turn into the other one. Okay. Let's see. Determine the molecular geometries, including all idealized bond angles for ClNO, where the N atom is in the center of the molecule. So we're going to put N in the middle, okay. Then we've got an O and a Cl that each wants to grab onto it. Now this makes sense because nitrogen usually wants to make 3 bonds, oxygen wants to make 2, and chlorine wants to make 1. So let's go ahead and figure out how this is going to work. Okay, we're going to have the central nitrogen guy. He's going to have 2 electron pairs of its own over to one side. It's going to have a bond right here with chlorine. Okay, and then he's going to have a double bond with oxygen, okay, which satisfies everybody's desires here. Okay. Now you could also think of these drawings of the bonds, right? If you want to do it in like classic Lewis notation, you can do it like that. Okay, that works. That works too. Okay. Since nitrogen has this extra bond pair right there, that means it's going to put the whole thing into sort of a triangle kind of thing. All right, and anytime, the whole thing sums up to 360 degrees, so 1/4 of that is 1/3 of that, sorry, is going to be 120 degrees. So that's probably about what we're looking at for this bond angle right here. Okay. Let's see. Classify ZeF4 as polar or non-polar and explain why. Okay. ZeF4, xenon tetrafluoride, okay, is going to tend to be have a square polar, square orientation, right? Xenon, remember, it's a noble gas, so it has 8 electrons in its outer bond. Usually it's pretty hard to get it to form things. You have to try pretty hard. So it's actually going to have these 4 bonds coming off of it like this with fluorine, each of which, of course, are only looking to make 1 bond. That's going to be flat. When it's flat like that, it's going to be nonpolar because although there is going to be intramolecular gradients in charge, right, they're going to be balanced out on either side. So it's not going to be able to do anything. Okay. Let's see here. They want you to figure out what's the orbital hybridization scheme. Okay, so in this particular case, in order for xenon for this to work, it needs to be able to have 1, 2, 3, 4, 5, 6 different orbital situations going on here. All right. So to make that work, we need to go to an sp3d2 situation, right? Where we're going to have all these guys are smushed together, right? So the way that this is actually going to look is you're going to have xenon in the middle with these 4 bonds coming off of it to the fluorine, right? And then you're going to have these clouds of electrons on either side. So it's going to have this sort of bipyramidal situation right there, okay? And consequently of that, right, you're not going to have any pi bonds, right? You only have pi bonds when you have a double bond between some. These are all single bonds, so these are all S bonds, aka these orbital hybridization bonds, okay? All right. Let's see. If you're doing it for xenon F2, though, the math kind of changes, right? XeF2, all right? And then you're talking more of a situation, right? Xenon, again, has 8, and these fluorines each has 2, so you need to find a way for xenon to be happy. Xenon's actually going to now have 3 electron clouds sort of arranged in a triangle around it, right? And then it's just going to have the fluorine bonds on either side of it, right? So this is now sp3d hybridization, okay? Gotcha, all right? The trick with this hybridization, you just have to keep track of how many electrons does everything have at start, because that's going to affect how many bonds it's going to be able to form, okay? Good stuff. All right. Now, that is actually pretty much all I have to go through with you. There are a lot more questions, obviously, in the practice exams, and I recommend that you run through as many of those as you possibly can. Certainly, if you do the ones in the book, you'll be in good shape. I recommend that you go and do some other ones also. You can find them on the internet. I'd run through several of these exams before you try to actually sit for the real one. When you do sit for the real one, you need to make sure that you're paying very close attention to what you've already been provided with, especially in terms of the periodic table, the equations, the constants, right? Anytime you see something in a question where you're like, I don't really, what does that letter mean? Is that an M or Z or what? Go look in your tables because it has this whole long list of all the constants and in all the different contexts that you can use, if you're being clever, to figure out what exactly it is the question is asking, okay? And there's a whole lot of different ones, all right? So you just have to be careful and make sure that you know what all of them look like before you sit for the exam. If you sit for the exam and you got your cheat sheet and they give it to you but you don't know what it means, then it's kind of pointless, isn't it? So make sure you know what all these little equations are talking about and what they could be used for, all right? With that said, I entrust you now to go forth and get a 5 on this exam. You will do just fine, and good luck.